Alright, welcome. So in this video, I'm just going to go through 3 facts that have to do with the gradient and the directional derivative. So my plan is to give you the 3 facts. You can sort of think of them as like theorems. And then after I provide you with the 3 facts, I'll go through their sort of proofs or why they work the way they do. And so if you're interested in seeing why these things work, you can stick around for that part. Otherwise, you'll get the facts that you need up front. So the first fact is that the gradient of f at a specific point a and b is going to be orthogonal to the level curve at that point. And this is true whenever the gradient is non-zero. So as long as we have a gradient that's not 0, whenever we look at that gradient, it's giving us an orthogonal vector to the level curve at our point. Alright, so our second fact tells us that the maximum rate of change for our function at the point a, b is given by the magnitude of the gradient vector at that point. So the idea is that if I look at any point on my function, all I need to do is find the gradient at that point, and that will tell me the maximum rate of change. So you can imagine you're standing at a point on the surface and you're trying to determine what the maximum rate of change is in any direction. You would look specifically at the gradient vector and its magnitude to tell you the maximum rate of change. Then our third fact goes along with this one, and it's that the gradient vector at a point points in the direction of maximum rate of change. So if you're standing at a point AB on your surface and you want to know which direction to go in order to walk the maximum rate of change, that would be the direction of the gradient vector at that point. Moreover, the gradient vector is orthogonal to the level curve, so if you were standing at a point, you'd want to walk orthogonal to the level curve to go in the direction of maximum rate of change. So these facts can be handy together if you're ever asked to find the maximum rate of change or the direction of the maximum rate of change. These facts tell you to use the gradient vector to do so. Okay, so these are 3 facts involving the gradient vector, and behind the scenes they actually have to do with the directional derivative as well. So I'm going to go through the explanations for each of these facts if you're interested, and that will be the remainder of this video. Okay, so let's go through the proof sketch or some intuition for this first fact. And this fact is that the gradient vector is orthogonal to the level curve. So the first thing I'm going to use to help us walk through this argument is that the directional derivative, when we are going a direction that is tangent to a level curve, is a value of 0. So you can imagine if we're on the tangent direction, we have a derivative of 0. This is similar to in single variable calculus when the slope of the tangent line is 0. Here, if we're going in the direction tangent to a level curve, that's going to have a derivative of 0. Next, this means if we have a unit vector u and it points tangent to a level curve at a specific point, then we can write out in math terms that the directional derivative of f in the direction of u is equal to 0 at that point a, b. So remember, we're trying to show that the gradient vector is orthogonal to a level curve. So we're going to use this fact that the directional derivative in the direction of u, where u is pointing tangent to the curve, is equal to 0 to give us the conclusion of our fact. Now, using the definition of a directional derivative, we know that if 0 is equal to the directional derivative, then 0 is equal to the dot product of the gradient of f and the vector u. So we know that 2 vectors are orthogonal specifically when their dot product is 0, and so this means that the gradient vector is orthogonal to this vector u, which goes along the level curve. So this means that the gradient vector is orthogonal to the level curve at the point a, b. Okay, so let's return to our second fact, and we'll go through a little bit of a proof for why this is true. Specifically, we're claiming that the maximum rate of change of our function at a point is the magnitude of the gradient at that point. Okay, so let's first suppose, since we're trying to find the maximum rate of change in this statement of the fact, let's suppose that we're trying to maximize the rate of change at a given point, and we're going to show that the maximum rate of change is specifically the magnitude of the gradient. So putting this into math, If we want to find the maximum rate of change, this means we want to find the maximum value of the directional derivative at this point. So we're trying to find the maximum value of the directional derivative at this point AB, and we don't really know which direction to go, we just know that we want to find the maximum rate of change. So let's look at what we can do with the directional derivative formula. So we know the directional derivative of f is equal to the gradient of f dotted with the unit vector that represents the direction we're going. But we can manipulate this a little bit. We know that the dot product of two vectors can be written as the magnitudes of those vectors multiplied together times the cosine of the angle between them. So I can write this dot product as the magnitude of the gradient of f times the magnitude of u times cosine of the angle between the two vectors. So remember here, u is just some unit vector that goes in the correct direction, the direction of the maximum rate of change. We don't know what it is here, but we do know that it's a unit vector anytime we're using the directional derivative. So the magnitude of u is 1. So I can rewrite this statement as just the magnitude of the gradient of f times cosine of theta. Now remember, we're trying to find the maximum value for this directional derivative. So we want to find the maximum of this product we have here. Well, the gradient vector is sort of fixed. It's given by the function and whatever point I'm at. So I can't really control it. I can't make it the maximum or the minimum. Like it just is what it is based on the problem. However, I can change the angle between whatever direction I'm going and the gradient vector. So I can change theta in order to make this cosine of theta the maximum amount possible. Since I'm trying to determine which direction to go in anyway, I want to pick the one that makes this the maximum value. So the maximum value for cosine of theta is 1. That's the maximum it could possibly be. And so if we put in 1 for cosine here, we're getting that we just have the magnitude of the gradient of f as the maximum of our directional derivative. Thus, this tells us that the maximum value of the rate of change at a point A, B is specifically the magnitude of the gradient at that point. So the specifics about what u is, which direction we go, is what we do in fact 3. This fact is just about the magnitude of the gradient being the maximum rate of change. So going on to fact 3 tells us that the gradient at a point is the vector that goes in the direction of the maximum rate of change. So this gradient of f is specifically our vector u that goes in the direction of the maximum rate of change. So let's write out that argument here. So from the previous argument for fact 3, we know that the maximum rate of change in a direction, that direction being the unit vector u, occurs when the cosine of the angle between the vectors is equal to 1. Remember here that theta is the angle between the unit vector u and the gradient of v. So from this, we can conclude that theta must be 0, since 0 is the angle that will give us a cosine value of 1, and so the angle between the gradient vector and u is 0. This means that the gradient vector points in the same direction as u, which points in the direction of the maximum rate of change, and so we can conclude that the gradient vector points in the direction of the maximum rate of change. Okay, so there we have it. We have 3 facts involving the gradient. We have that the gradient at a specific point is orthogonal to the level curve at that point. We have that the magnitude of the gradient represents the maximum rate of change. And we have that the gradient points in the direction of the maximum rate of change. Hopefully those proof sketches with a little bit of intuition helped you understand why these things are true, and now you can go use them in other problems that involve the maximum rate of change or finding orthogonal vectors. Thanks so much for watching, and I will talk to you in the next one.